טוב, שלום, ברוכים הבאים. אנחנו הרצאה שלישית. Good. Okay, thank you. So, we finished Mark Sweep. Compaction, we did two fingers, Lisp 2 and Yonkers. And we need to do the rest. And we'll also, let's see. Okay, we also will do copying after that. Okay. So we're doing compaction, and we've done until Yonkers, and we have to do the rest. Remember, the generic task is that we have to move all the objects to the beginning or to some small number of piles of objects, and we want to modify the pointers. So it's important to modify all the pointers because objects move. So we need to do that. So we talked about the Lisp 2 algorithm. Okay, we talked about the two-finger algorithm, which is very simple. We talked about the Lisp 2 algorithm, and the way it works is that in the first pass, it goes and it installs forwarding pointers. You remember the forwarding pointers in each object will be used to show where it moves. Then in the second pass, we go over all pointers and we fix them to point to the new location of the referent object. And then in the last pass, we go and we move all the objects. The pointers are already correct. We just need to move them. So this was the Lisp 2 algorithm. It's very simple. Keeps the order of objects, but it's 3 passes and it needs an extra space for each word, for each object. And then we studied the threaded algorithm, and it was good in the sense that it didn't need any additional space, and it only needed 2 passes, and the object size was not restricted, and it was sliding. So everything looked excellent, but we do not know how to parallelize it. So it was used until maybe the beginning of the 2000s, where actual parallelism became very prevalent all over, widespread, and then people looked for alternatives. So we're going to talk today about how to do parallel compaction. The first one was by a group in Sun. Again. Okay, so parallel compaction, Sun's version. So you just take the Lisp 2 thing and you parallelize each pass in this algorithm. Almost naively, but what you do is you divide the heap into regions. You divide the heap into regions, and each thread takes a region and just works on it in these 3 passes. Oops. So you first need to install forwarding pointers, right? This is the first pass. So you do it. Actually, let me go into this picture. It will make it easier. So first, what you're going to do is you're going to compact inside each region, which is not excellent, but for that they did this kind of nice observation that you can, in odd regions, you can move right, and in even regions, you can move left, and then you get half the number of piles eventually of compacted objects. So this is the picture, and what happens is like a thread takes region, and then it compacts the objects to one of the size according to even odd number. And then it does this with these steps. So the heap is divided to n regions, and n is the number of threads that are compacting. And so and they don't do a uniform division because they say some regions have a lot of objects, so it will be a lot of work. Maybe we'll take a smaller region if there's a lot of objects, but forget about it. For simplicity, just think of even the same size for all the regions. And then each region is compacted independently. Um, so here it says how you work in parallel. So in phase one, each thread grabs the region, it takes the region to work on it, and it installs forwarding pointers. So, all the objects move inside the region, so you know when you go over them where they move. Okay, so you can, according to the space that's occupied before them. So you go over all these objects and you install the forwarding pointers that say where they're moving inside the region. And after all the threads are done with phase one, all of them are done. All the heap has forwarding pointers. You go to phase two, and then each thread takes a region and it updates the pointers. So it looks at the pointer. The pointer maybe points to some other region, it doesn't matter, or to its own region. But all the objects in the heap have forwarding pointers. So it is possible to update the pointer to the new location of the referent object. So this is the phase two, and each region is done by a different thread. And in phase three, each thread again takes a region and just moves the object, and it's inside the region, so there's no need to cooperate between threads on any of this. But yeah, okay, but they don't. So if a thread finishes phase one, it doesn't go to phase two until all the threads finish phase one. So, and so first all the threads finish phase one, and then the first thread starts phase two. There's no like mixing of threads doing phase one and other threads doing phase two. There's like a barrier between moving from one phase to the next. Okay. Um, okay, this says this. Now, when you do a phase, you have to get a region and be responsible for it. For that, you need synchronization between the threads so that each one gets its own region properly. After that, you don't need synchronization. You just work on your region and you don't need to cooperate with other threads. So there's little synchronization, and that's it. That's the basic algorithm. So, any questions on this? Yeah. Right. So this is the only phase where I go out of my region. So here, just to decide the addresses and put forwarding pointers, I do it inside my region completely. And moving the object is done inside the region completely. Here, I look at other regions, but I only look. I don't touch it. I don't make any changes in other regions. I only look at the forwarding pointers in order to decide how to fix my own pointers. So there's no significant there's no need for cooperation, but there's also no significant interference between the different regions. Um, what may bother you is that suppose one region has a lot of work and the other regions are easier to handle. And then what happens is that threads finish their work and now they have to wait for this thread that is working on this very busy region. And that's right. So, but you can never really do it properly. There's always a problem of like to balance the work between the threads, and we'll talk about that. Yeah. In here, because I want to update the pointer, so I look at the pointer and it points somewhere. It could point to other areas. So it's okay. I look at the other area, I see the object. It has a forwarding pointer because phase one is done. But I can just read it and fix the pointer that I'm handling. What so what I'm doing here is I'm trying to compact the objects, right? When I'm compacting the objects, there are there are other objects that point to them. There are fields inside other objects that point to them. After compaction, each pointer should point at the same object that it pointed earlier. So if I'm in the beginning of the heap and I point to the end of the heap, this pointer still has to point to the same object. It moved within its area, but I have to point to it. I cannot point to something else that's within my area. I need to keep the semantics of the program. I need the program to behave the same. And so the pointer should point to the same object. And so if I'm pointing to an object in another area, the pointer will still point to a object in another area, in the same area, but in a different location because it moves within the area. Yeah.
הסיבה שאותו פרק לא עושה כל השלוש שלבים זה בשביל שנוכל לעשות את העצירה הזאת עד שכולם יסיימו.
Yeah, it's not, you could say a thread grabs an area and just sticks with it until the end, right? It's not so bad, but yeah, I guess it's not so bad, but you have to separate the phases. You cannot let a thread start. So if a thread has region one, it can do it in phase 1, 2, and 3. But after finish phase 1, it has to wait for all the threads to finish phase 1. This has to be done. Everybody has to know that all the others have finished phase 1 before they start phase 2. So maybe you can tell me.
Because if it wasn't moved and you don't have the forward pointer, then you point to an object, then you won't get its new position.
Exactly. So between phase 1 and 2, I have to be done with phase 1 because when I want to fix a pointer, if I don't have a forwarding pointer because someone did not finish to work on that region in phase 1, I cannot do my phase 2. So I must wait for everybody to finish phase 1 before I move to phase 2. Why do I need to have to wait between phase 2 and 3? Why can't I start phase 3 while others have not finished phase 2?
Because after the thread needs to know where to search for the pointers.
Exactly. Exactly. So there are some threads here that are looking at my objects to see where they moved. If I move them and they don't know, they don't get the information of the forwarding pointer, they cannot do their own work in phase 2. So I cannot start phase 3 because it will destroy the shape of the objects with the forwarding pointers. It will destroy it for those who are still in phase 2. Yeah.
I have a question. If you don't split the phases, but you create one phase and you have a flag that for each phase or a way to indicate it, would adding that overhead in the header be worse than waiting between the phases? But I mean, if you try to go to somebody and then
You mean between phase 1 and 2? Instead of waiting for everybody, I say I will wait only if I need it. If I don't see a forwarding pointers, then I will wait for it to be installed.
your region and you go over your region again and again.
Yeah, you could extend it. I think you could do that. They don't do that.
Like with a whale loop, go over your elements in the region until everybody, and then for each one fix everything and kind of.
Right.
Some other thread.
Yeah. You could extend it. It's a nice idea. It will let you maybe let some thread run phase 2 faster than it would have if it waited. But in the end, if there is a slow thread, everybody will have to wait for him before phase 3. You cannot do it with phase 3 because you break the heap structure for phase 2. So here you have to wait. So if you let some thread run very fast and all the other threads are slow, eventually the fast thread will have to wait between phase 2 and 3. So it's a nice idea and it works, but eventually it will not give you the performance you want at the end. More questions? Okay, cool. Okay, so this is how it works. Properties, it runs in parallel, it has good scalability. Scalability means that if you add more threads, it will run faster. It keeps the order of objects, and but with these good things, there are the problems. Objects are not fully packed because they're packed into several piles. And we need an extra word per object, like in the Lisp algorithm. There are 3 passes, like in the Lisp algorithm. And there is coarse grain load balancing. So if I have four threads, then if one of them is delayed, everybody has to wait for it. And since these are large tasks, these are a quarter of the heap is done by a single thread, then this is a maybe if someone is delayed, everybody will have to wait for that. I would prefer small tasks where everybody is doing a small amount of work. So if he's delayed, he's delayed for a little while, and others can work on other tasks. And this is not good for load balancing, this manner. Okay, so let's move to the next method, our last for today. This is by IBM, and this was led by Diab Abu Ayad. So this is going to be a parallel compaction algorithm. So in the threaded algorithm, we already had the good properties that we want, like two passes, no space overhead, everything looked perfect, but we don't know how to parallelize it. So this is going to be a parallel. Objects are going to almost be packed to the bottom. In a Lisp 2, we have several piles. Here, everything is almost going to be packed. We'll talk about the almost, back to the beginning of the heap. Space overhead, we have something that's usually smaller than a forwarding pointers. We'll have something, space overhead that's not big, and we'll have two heap passes, and each of them will be executed in parallel. So we'll have almost everything that we want. Okay, so the way he said we're going to do it is we're going to split the heap into areas. Say here in this example, he takes a 640 megabyte heap and he divides it into 64 areas. So areas are large, right? It's not like a quarter of the heap, but it's a large chunk. And now, within these areas, what we do is we want to move everything to the bottom, but we want to do it in parallel. So we'll start working on these areas. So each thread is going to pick an area and then start moving stuff to the beginning inside the area. So maybe these two threads, there are two threads, they took these two areas and packed to the beginning of this area. Now, when a thread comes and wants to compact this, instead of compacting it to the beginning, it will compact all these objects to the free space that is still left in the first area. So this is going to be the idea. Here is, so these pictures, the Ab did, these slides. So if maybe the first threads are compacting the orange and the blue, then the third thread and the fourth thread just take the brown and the green and they add it to the vacant spaces in the orange and the blue. And you see here that it's not completely packed. This is not ideal. There's a hole here, right? But if there are more areas, then there's more chances to fill the spaces in these places. And then the if, painted this, depicted this. He said, if you move all objects to many areas, you're almost able to fill everything, and then it's packed quite well to the beginning. So this is the idea with the areas. Yeah.
Understand? You said that each area compacts itself, and then if there's more room, areas compact into each other, or if
Yes.
so
That's the process. Yes. Okay. So how do you pick an area size? So he said it's not that sensitive to the size, and usually you will do well. So if you really do something small, then you will not have holes in the heap, and the load balancing is going to be very good. Like if we have small tasks, then at the end, when everybody has finished and there is one still going on, if the tasks are small, then we don't have to wait a long while. So in load balancing, if we have small or medium-sized tasks, we'll be okay. If we have very large areas, then maybe someone who is dealing with a large area will have to wait for him. So the load balancing will not be good here. In terms of preserving allocation order, so within the area, the allocation order is preserved. Between areas, maybe it's not, right? Because I move each area to another location. So if I have like large areas or medium areas, most order of most objects is preserved. At the boundaries between areas, I will not preserve it. If I have very small areas, I don't know, if I have an object per area, then I will have no order at all. But if I have small areas, I will have not as good allocation order preserved. And then in terms of holes in the heap, so as we saw in the first picture, if I have very large areas, then I will have holes. But if I have small areas or medium-sized areas, then it will be okay. Okay? So he says it's not very sensitive. How do you do it? In the first phase, what is the process? You take an area to be compacted, you find the lowest area with space large enough to compact into, and then if none exists, you just compact to the beginning of your own area. If there is another area to compact into, then you just compact into that as your output area. Um, Now, when you move the objects, you create a side table. So what we tried not to do in all the previous algorithms is use additional space. Now, in year 2000, space was more available, and he said, let's use some space outside. And eventually, this space, he did it so well, we'll talk about it, that it was really small overhead that was probably less than a forwarding pointer word per object. Um, so when moving the objects, you create a map outside that if you have an old address, it tells you what the new address is. This is like a forwarding pointers outside the heap. You take an old address, it tells you what the new address is. You can start by thinking of a hash function or something like that, but we'll do it better for this purpose. Yeah.
כאילו בהתחלה הוא מסתכל מחוץ לאזור שלו, ורק אם הוא לא מוצא הוא עושה קומפקט.
In terms of finding the output area to compact to, you start by looking at the lowest areas and you see if they have enough space to move your objects into there. If not, then you compact within your own area.
כי כאילו בשקפים הקודמים אמרנו קודם עושים קומפקט באזור שלנו, אחרי זה נכון כאילו אולי אני מבלבל.
If you look at this, or maybe at the larger one, I start with this. I started looking at lower areas if they have space, but there are no lower areas, so I just used my area. The same for this. It looks at this if it has space, but this is not available as output because it was not yet handled. But when I do these two, and now I go to this, I found that the space that I have can move into here, and so I use this as an output area. Okay, this is what he says. Okay, so I need to. So after I do this, all the objects have moved, and I have a mapping from all addresses to new addresses. Then all I have to do is the second phase. Each thread just takes an area and fixes all the pointers. I can fix the pointers because I have this mapping from old addresses to new addresses. So I can say I have pointer, it points to the old address. I have a mapping that tells me what the new address is. I just use it and fix the pointers. Okay, naively, you can think of a hash, okay? I have an old address, the pointer points to it, I get the new address, and I fix it. So in phase 2, I fix all the pointers. Yeah.
בשלב הקודם, מבחינת המקביליות שאנחנו עובדים עם כמה טרדים במקביל ומנסים כאילו לתפוס את אותו מקום בדרך אחד, אם לא מתאים, אז אנחנו נתעסק בזה גם, או שזה מתחת מתאים.
So when where is it? So I need to find the lowest area with enough space, and maybe there are more threads that are looking for the lowest area with enough space, and we're fighting against each other. We need to coordinate and synchronize. We will not get into the details. There are data structures that allow you to synchronize very efficiently on grabbing something. But for the sake of, if you just studied operating systems and you know what a lock is, think of it that I take a lock of the table of spaces. Each space just tells me how much space is in it, each area, how much space is available in it. I take the lock, I go over that, I take my own area, I mark that I take it, and then I release the lock, and everybody knows it's mine. That's a very coarse-grained way to do it. There are better ways. There are courses on parallelism. If you want to get a deeper, understanding of how to do parallelism well, data structures that let you do good parallelism. But we will not get into concurrent data structures in this course. We'll assume it's possible. Okay. So, so generally, there is this question of synchronization versus load balancing. So, like you said, if I want to pick an area, then picking the area needs to synchronize. So if I have very small areas, then each time I'm picking one, I'm working a small amount of time. Shortly after that, I need to get another area, and then I have to synchronize again. Then there's lots of synchronization. But if I have large areas, I synchronize to get the area, and then I work for a long time until I need to synchronize again to get the next area. So synchronization depends on the size of the area. So if the area size is large, then synchronization overhead is small. And that's like, and on the other side, if the task size is large, then the load balancing is not good because the last thread that is working and everybody is waiting for it has a large task. So he may do it for a long time until we can all finish. So it's good to have a small size tasks for load balancing, but it's good to have a large size task for synchronization overhead. There's this trade-off, and we have to deal with it. You don't want to take extremes. And usually we take small size tasks because we do want to keep the load balancing reasonable. And synchronization has been developed for, we have good ways to synchronize. We are by now. So we usually take small task sizes, so small areas are good. Okay. So now we want to do the fix-up map. So we said like, you could naively use a hash, but it is not a general mapping. If I use the hash for each object, I would need to keep an entry in the hash that says for the old address, what would be the new address. And that's a lot of space, right? I would need an entry in the hash for each object. That's a lot of space. And the app managed to build a way to map it more shortly, succinctly. So this is the way he works. Okay, I will now describe his thing that replaces a general mapping. Okay, so he looks at the heap as a sequence of blocks, and the blocks are much smaller than areas. So you can think of blocks as maybe a quarter of a kilobyte, and an area is 10 megabytes, and this means that it's like 40,000 factor. So there are 40,000 blocks in an area. Areas are large and blocks are very small. Okay? So there are all these blocks, and these blocks help us map all to new addresses. This is the goal. To get, I have an old address, I have to compute the new address. This is my goal. So the information is going to be recorded per block and not per object. And so all the objects in the blocks are moved together. They are compacted, so maybe they take more space and move to a smaller space, but they are together. They keep the same order. If I have, I don't know, 5 objects in a block, they are compacted together and remain adjacent to each other. So I'm going to record less information per block, but I have to do some computation to find where each object moves. So in this hash function that we thought of, I have an old address, I go to the hash function, I get the new address. Here, it's going to be, I know where the block moves, but inside the block there are several objects, and I will have to work a little bit to understand where each object moved within the block. So this is how it looks. So I have a block, and the first thing I'm going to keep is a block table. Each block where the first object in the block moved in the new heap. So there is a compaction, objects move, and I'm going for each block, maybe there are several objects here, but I'm going to say the first object here moved here, and I'll have a pointer to where the first object moved. Okay, so for each block, I have a pointer. This is one thing I keep. So instead of keeping for each object where it moves, I keep for each block where it moves. Okay, so, okay, this is the first thing. Now, I'm going to also use two bitmaps. There is the old bitmap, like before the move, there is a bit wherever an object starts before the move. And in the new bitmap, there is a bit where an object starts after the move. I think I have a drawing that I usually do on the whiteboard, but let's look at it. So I have the heap before the compaction and I have the heap after the compaction. And this is a block. It has three objects, A, B, C, and they move here. Now, this doesn't have I don't care about blocks here. But what I want to say is that this block moved to here. Okay, so I have in the block table saying that block 234 moved here. Okay, it means that the first object in this alive in this block is exactly here. Others are just after that. Okay, and the old bitmap says here starts an object in before the move, here is an object starting in here, and the new bit will say here is an object starting here, here, here. Objects are starting. Okay, so I have bitmap before the move and bitmap after the move. Now I want to know where B moved. How will I know? So I have this old bitmap, new bitmap, and I have something tells me where the block moved. So if I want to know where A moved, then I can just look at the where its block moved, and then I know where it is. How do I know that A is the first in its block? No, 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 no. A is like a general size object. I
ההיפ עצמו לגרעין מסוימים, אז אתה יודע שהפורמולה בעצם מתחיל.
לא רוצה I do not want to force myself to divide the heap to specialized size.
If you add it 20 by 5, you know that each form it starts some new area.
The areas are of constant block or areas? Well, you can speak Hebrew. I will answer in English. Right. That's. I suppose all of them were the same size. Not all of them are alive. Blocks. The blocks. The blocks. These blocks. I know where they are exactly. Yes. So I know. So A. I can tell that it's block 234 because I just divide its distance from the beginning of the heap by 256. And then I know that I'm in block 234. That's very important. So I can just look at the address, divide it by 256, meaning getting rid of the first 8 bits. So I shift it. And then I know in which block it is, and I know that this is where the first object in this block moved. But how do I know that A is the first object in this block?
Can't we just read the block? I mean, we said it's like 260
You can read it, but how do you know where an object starts?
maybe put כמו סימן דרך כזה בפיטים
So maybe we have this information here. Yeah, the old bitmap. This would tell me, right? I come to the beginning of the block. I want to know who the first object is. I look for the first bit that is set. This is the first object in the block. So if the first bit in the block is here in the old mark bit, then I know that this object moves to the pointer of the block in the block table. Okay? Now, if I want to know where B moved, okay, how do I do this? First of all, I want to know what is its ordinal number, מה המספר הסידורי שלו. Which is it, like first, second, third? How do I know that? What? Inside the block, yes. How do I know? Exactly, I count how many bits there are. So C is the third bit, so it's the third in the block, right? So I want to know where C moves. So I know that the first object in the block moved here because I know in which block it is by shifting the address by 8 bits. So dividing by 256, I know which block it is. So I know the first object moved here. Now I go through the old bitmap and I see that C is the third object. How do I know where C is? Exactly. I look at the new bitmap. So this is the first object that moved. I go until I find the third object in this, block. And this is C. This has to be C because it's the third. In the old bitmap, I find what is C in this block. It's the third. And then I see where the block moved. And now I start looking the new bitmap and I'm looking for the third bit. And when I find the third bit, I know this is the place where C is. So this is going to be the way that we keep this mapping between old to new addresses. So I'm just going to keep pointers to where the beginning of the block moved. And then I'm using these bitmaps in order to find out inside the block where each object moved. Question, yeah?
So
Yeah.
this is what we do in phase 2, right? And the new bitmap we create in phase 1. And that's why we have it.
Right. So in phase 1, we build all of this. How do we build it? So if we move a block, we have to fill this value, right? And the old bitmap already exists, and we build the new bitmap. Each object we move, we set a bit in the new bitmap. Yes. So in the first phase, we build the new bitmap and the block table. In the second phase, where we need to know for each old address where the object moved, we use this algorithm. We get an object, we find out which block it is, we go to the offset table, to the block table to find where the first object moved, and then we go to the old bitmap to decide what the ordinal number of the object is. And then in the new bitmap, we find exactly where it is located after the compaction. Yeah.
Why do we use blocks in the second phase and not the areas already done?
So this is the question about the size of the block. So if we did like a huge block, it would be an area. But note that the amount of work that we need to do depends on the size of the block. So if there's only one object in the block, this is really easy. We see that it's the first, we look at here, and we're done. If it's the seventh object, then we need to find where the block started. We need to find that it's the seventh by going over this and looking. And then we need to go over this and start looking for the seventh. This takes time. If it's,
It's a trade-off between Switzerland and Zikora.
exactly, it's a trade-off between time and space. If we have very large blocks, then this table will be very small, right? Only the number of blocks here. But we'll have to do a lot of work to find out if we have, I don't know, thousands of objects, just to find the 1005 bit in this bitmap will take a lot of time. So there's a trade-off, how much time we'll have to do in order to compute the new address as against the number of entries in this additional table that we need to keep. Yeah.
When do you say that this is redundant and you create and the heap after becomes the heap before and the new bitmap becomes the old?
So the compaction so I stop the program completely. I do marking, I do compaction, and after that the program continues to run on the new heap. It's like completely separated from the execution of the program. I run all this algorithm and then I let the program run again. Yeah.
Case of an object being split into blocks.
Like going over the boundary of a block. Then you have to decide, like, and what the app did is if the object begins in one block, then it belongs to that block. So if you have this block and maybe C continues after the end of the block, C is still in this block. That's his decision.
And then you would point to somewhere else.
The beginning of this block would be where this moved.
No, I was thinking about the other block when C moved to the other block, at the beginning of the other block also moves a bit because the accuracy.
So suppose I have like this is a block and this is another block, and I have here maybe A and I have B who is spreading to the next block, and then I have C. Then if I look at the old bitmap, right, this is the situation. So this would be part. These two would be part of this block in the computation, and C would be the first object of the next block. So it will not be a problem to the. Okay. Yeah.
What if we have A, B, and C, and the first block is so tied together already that we can't, after moving, get C but still be in the following block?
A, B, and C. So I have A, B, and you want to put.
The next block. Yeah, and there's no compaction that will make it so the C won't be in the next block. What happens to
So in the heap after, I don't care about the block structure. I just move them. The only use of the blocks is to know, where each object. It's like a mapping, and there is no blocks here. I don't care.
so we just well, D won't be at the beginning of its block during move, and we know that.
No, it will be. There's no blocks after the move, so there will be no problem. So suppose here you have a D. This is what you're thinking. D will be the first, and the table that will say where this block starts will tell you where this guy moved after the. I don't care about block structure at the next, like in the new heap. So yeah.
מה נשמע במקרה קצה, אז נניח שזה הבלוק השני, היהודי, אז הוא מתחיל עדיין הוא מתחיל באמצע של B כביכול, או שהוא מתחיל ב-C? כאילו מבחינת
So after I move, okay, so this is suppose it moves here. A, B, and C will go to some place in the new heap. I don't care about blocks here. It does not serve me in any sense. I only care about blocks before the move. In any of this computation of where objects move, I only care about blocks before the move. After the move, I don't care about blocks.
כאילו מה שקורה לפני שאנחנו עושים את השינוי, אז הבלוק השני הוא מצביע כביכול באזור שלי.
So here, the offset table, this will point here, and this offset table will point to C. Yes, to the beginning of C. It will not care.
Not the address. You pointed to the beginning of the first object of the block, not the address that we said would be the beginning of the block.
The address of the first live object. That's yes. This is the definition of what I see here. The address after the move of the first live object in that block. It's like where the block was compacted into. Yeah. There's no blocks. After the move, there's no blocks. Ignore the blocks. It's just the objects. Yeah.
Before we say that we know the address of each block where it starts.
Yes.
But the pointer is there to point to the object, not the address of the start of the block. We understand.
Okay. Okay. Yes. Cool. Okay. Let's go on for 5 minutes so we don't break in the middle and then do a break. And remind me to upload the presentation afterward. Okay. So this just says what we said on the drawing. To calculate, given an old address, I find the block it is in by removing the least significant bit and looking just at the most significant bit. I shift it. I use the block table to obtain the new address, so where this block has moved, the first object in it. I use the old bitmap to see what number, the ordinal number of the object is in the old block. It is the same number in the new block. So using the new bitmap, I find the relative new location of the ith object after the move, and that gives me the new location of the objects that was moved. Cool. Okay. So here's an example, but we did it. Okay, we did it already on the other drawing. And like you already said, it's a space versus time overhead. The space overhead is a pointer per block. And if I do small blocks, then I'll have lots of these. If I have large blocks, I'll have a few of these. So they used 256, and that gives them 3.1%. The two bitmaps, each of them is 1 over 64. Both of them are 3.1. So overall, it was 6% overhead for all these structure. Now, the old bitmap is something, this is the marking, this is the mark bits, because I do the marking and I see where all the objects are alive before the compaction. So the old mark bits are actually prepared by the marking procedure before the compaction, and it's used for the garbage collection. So you can say that 1.6 of this is already there, even if you don't use compaction. So so this was okay. Block size trade-off we talked. And the algorithm ideas that we had is first we use these areas and compact into an area and from one area to another area, and that's how we move everything in spite of parallelism to the beginning. We keep an auxiliary table, and that's how we don't need 3 passes, because we have outside table and we don't overwrite things that we need inside the heap. So we move from 3 passes to 2. And the auxiliary table, we don't use hash functions. We use these blocks in order to make it short, and then we are better in space. So these are the 3 algorithmic ideas that Diab had. And properties, you compact almost to the bottom of the heap. The order of the object is essentially preserved up to between areas. Good parallelism, small contention, and the space overhead is even lower than forwarding pointers. And so I think we're done with the algorithm, and we'll do a break. I will show you a bit of numbers of performance after we come back. So let's talk about the measurements. So when they evaluated how good this is, so they compared. So the previous algorithm that was used in Java at the time was the threaded algorithm, and and it is not parallel. So the first measurement that they did was to compare this new parallel algorithm to Yonkers, but they did it on a single thread. So they restricted it to run only on a single thread. This was, not using some of its property, but they compared it. And then they took the fully parallel algorithm to see what happens if you run more threads and if you get scalability. The platform was some Unix that was then popular. Benchmarks. I don't want to describe them, but I will. Let's look at the measurements, and I will try to explain. So the first thing is SpecJBB. It was a very important benchmark at the time. It was like an industrial thing that had warehouses. So for each warehouse, if you add a warehouse, it used an additional thread. So this thing can be looked at as the number of threads, but with each warehouse, also the heap grew. So you get more threads and larger heap. when you go through the X values. The Y value said the time of the compaction. So, of course, with larger heaps, you get longer compaction. And this is what you see here. And now, this is the algorithm of Diab. It's parallel, but it's run on a single thread. So it would be a fair comparison to the threaded algorithm that runs on a single thread only. So what you can see is that as the heap grows, you can see a larger distinction between the two, and Diab's algorithm is more efficient than the threaded algorithm, which is good. And then he said, now I add parallelism, and now you can see this is what happens. So what you see is the speed up. It means it's the same x-axis. You get more threads and more for the benchmark. I'm not talking about the compaction. The benchmark gets more threads and larger heap. For the compaction, what they do is they use 2 threads, 4 threads, 6, and 8 threads. So it's never perfect. So if you put 8 threads, it will not be 8 times faster. What you see here is how faster it was. For 2 threads, it was 1.75, which is very good. All of this is very good. You do not see such speed ups usually. For 4 threads, you get around 3.5 speed up, which is also very good. And with 8 threads, you get basically maybe 6 speed ups, 6 times the not using parallelism. So without using parallelism, it's better than the threaded algorithm. And if you add parallelism, it goes a lot faster. So it was very good measurements. And okay. And something else, you can measure the behavior of the benchmark itself without the compaction. So what this tries to measure is maybe I spoil the order of the heap, and then when I do the order of the heap wrong, then the benchmark itself will run slower. This is what happened with the 2-finger algorithm when you tried to run it. So the benchmark itself ran worse because we messed up with its locality. So what you want to measure is whether the new algorithm, because there are areas, it doesn't do exactly a sliding moving. Between areas, the order is not kept. So you want to see that this order is okay for the benchmark. So he ran the benchmark without counting the time taken for the compaction itself, just for the benchmark. And what you can see is it's exactly running in the same time as it runs with the threaded algorithm. So this is important to see that locality is not destroyed by the new algorithm. And nothing is seen because of the new order that we get with the new compaction algorithm. So this is also excellent. There's another benchmark. I will not go into it, but so to conclude, Diab's algorithm, IBM's, is more efficient than the threaded algorithm that was used before that, and has a good speed up. So parallelism help. If you add more cores, you get better performance, and compaction quality is as good as the threaded. It's as good as sliding. Okay, yeah. There were 8 cores on the machine. When was it? It was 2005, maybe. I don't remember exactly. That was a machine that was hard to get. I mean, not easy to get. Today, maybe your phone has 8 cores. It's a very different world. Today, usually you would see comparisons where it's 64. You can ask why it goes down after that. That's also interesting, but you always see it with parallelism. When things get, you have more tasks than what you have hardware, the number of cores, and things start to fight with each other on synchronization. Threads go out in the middle of doing something, and other threads cannot work with it very well. I don't know what here specifically happens, but this is very typical. Usually it goes a lot worse when you go beyond the number of cores that you have on the hardware. Okay. Okay. And there is, so this algorithm was used for a long while. There is another algorithm which is called the compressor, and it has a single heap pass plus a single move on a bit table. We will study it towards in the second half of this course. It's more complicated, and it's the basic is not complicated, but parallelizing it is a little bit more complicated, and I want to delay it to a later time in this course. And that's almost the final word in this area. Almost, because the one who checks your exercises, Tomer Corey, when he studied this course, he had an idea of how to improve the compressor and IBM. And he has a paper about that, which is not clear if it does better than the compressor. It is still being tested, so we'll see. But the compressor is almost the final word on this, and we'll talk about it. Okay, cool. Okay, so to conclude, we've studied two fingers, Lisp2 and threaded as single-threaded algorithms. And then we went into parallel compaction and looked at Sun's compaction of the Lisp2 and IBM's compaction. We still need to talk about the compressor in a later talk. And we talked about efficiency, space overhead, parallelism, compaction quality, locality. That completes compaction. Any questions? If not, then I will move to copying. Okay. So copying is one of the classical algorithms. We're going to work with it. The idea, we talked about it in the first class. We have two semi-spaces. This is how it's called, two semi-spaces. We start by doing all allocation in one semi-space. And then when there's no more space, it's exhausted, we take all the live objects and copy them to space two, the other semi-space, and then we can allocate in the second semi-space. When that's done, we flip the roles and we copy from the second to the first. And so each time we have a reserved space for the next collection to copy into, and we just use it like that. This is a drawing of that. So suppose A and C are reachable from the roots, and we start with working in this space. Now we'll reverse the roles. This will become from space. This will become to space, and we'll start copying. So we'll go through anything that's reachable and copy it here, and of course fix the pointers. And finally, we're going to fix the root pointer to point to the two-space copy, and then we're done and the program can start running again. And now the first semi-space will not be used. It will be reserved for the next collection, so that we'll be able to copy back everything that's reachable in the next collection. Yeah.
נחזור רגע לשקופית אחורה, יש סיבה למה A לא יהיה בהתחלה, כאילו ממש.
A is in the. Ah, you're saying why is there green space? Why is it not all?
ספציפית, כאילו נגיד האיבר הראשון, אנחנו תמיד נתחיל
I mean, the program, the one that decides where the pointers are and how they look is the program, which we have no control over. So tomorrow, the next step you run by the program can change this pointer to point here or to wherever it likes. This is the code of the program. We do not know what it does, as long as it behaves according to the rules of the programming language. But we do not decide where the pointers are. We just see it and have to work with it. Okay. So the naive algorithm, and maybe you can tell me how to make it less naive, is in pass one, I trace all the reachable objects and I copy them to the two space. And I install forwarding pointers. So if you look at this, if I move A to here, I can put a forwarding pointer in from space telling me where this object is in two space. That's fine. I'm not going to use it anymore. I can overwrite it. I put a forwarding pointer. Okay. So I just go over, I do DFS over all the reachable objects and keep forwarding pointers where I move the objects. And in the second pass, I go through to space. All of the pointers are pointing to from space because I just copied stuff from space with pointers to from space. So all the pointers are to from space. I just go pointer by pointer. I look at the forwarding address and I fix it. And so it's two passes, which I don't like. I want it to be one pass. And also, I have a mark stack for the DFS, which I don't like. Not only I keep a reserved half heap that I don't use, now I also have a mark stack. So this is a lot of space usage. And there is a way to remove the mark stack, to not use an additional mark stack. And there is a way to use one pass. So if you have any ideas, then I'm happy to hear. Yeah. If you're lazy, what do you mean?
Well, we can put the forwarding pointers in the from space and leave them there and don't do anything with them. Then you have an extra indirection, but you can still reach all the objects, right? From the roots, because you don't use that space. So if you just leave the pointers there and don't do anything, then
In from space, I do leave the forwarding pointers, but you're suggesting to.
so
Yeah, there is unused space. That's clear. So
during the first pass, we install the forwarding pointers there, right?
yeah, copy, install forwarding pointers.
Yeah, and then we can not do anything with them, and everything should still work, right?
You're saying let the program work without fixing the pointers, and the program should know about it when it works. This is so. I mean, it's correct, but usually in real systems, you work for a long while, then you do a garbage collection, and then you work for a long while. You don't want to put an overhead on your regular program work because eventually this makes the entire run be longer. Interesting idea, but in practice, we will not want to extend the regular work in order to save on the garbage collection work. Okay, yeah.
נכון,
Sure.
בפעמים הקודמות אז בעצם חילקנו את זה לפסים בשביל להימנע נגיד כתיבה וקריאה לאותו מקום או משהו כזה, אבל עכשיו אין לנו את זה. כאילו יש לנו
Okay.
חלק אחד שהוא רק לכתיבה וחלק אחד רק לקריאה.
Yeah.
אפשר עוד מנות פשוט לעשות את זה. ולא צריך את
You want to unite the two passes, but if I just look at this, I go to an object, I copy it into two space, and now maybe it has pointers that I want to fix, but how do I fix them? It's a good idea. Okay, but
כאילו לעשות את עוד
so I just let's concentrate on a single object. I move it. I keep a forwarding pointer. Now I have to fix the pointers. I want to do it at the same time. I have a pointer. What do I do with it? How do I fix it? Maybe it's pointing to something that has not been copied yet, and then I don't know how to fix it. Yeah, it's a good direction, by the way. Okay.
I
Yeah.
don't know if it works, but when you go down this trace and you find an object that you can't go down from it anymore, it doesn't have like any children DFS, then you copy it, fix it, and when you go back up the tree, then everything is fixed already because you do one pass over it.
Okay, that's interesting, and it may even work for. I mean, so you are still keeping the mark stack because you're doing a DFS, but you're doing only one pass. So when you go back, you know that you've already copied the children. So for sure you have a forwarding pointer and you can fix it. I need to. It's nice. Yeah, it's very nice. I need to think if it's working.
It does work if there are no cycles. That's what.
So if there is cycle, I get to the last level and then I have a backward pointer. I have a
Go in circles. If you trace and then you go back.
right. The DFS will stop when there's a backward pointer, and then I cannot fix it. Right. That's also a good observation. So it's a nice idea, but this is a good observation. If I have a backward pointer, then I'm dead because it's to grandparents, and I don't know how to fix it. Cool. Okay, nice idea. So now I will say how Cheney did it. He is really one pass, 2 pointers, no mark stack, nothing, just one pass and 2 pointers. Which after you see it, it looks so obvious. Then you don't appreciate it if you don't try to solve it yourself. So what he says, let's copy all the objects that are directly reachable from the roots to the beginning of two space. Okay, if something is directly reachable from the roots, I copy it to the beginning of two space, and then I just go over two space. Whenever I see a pointer to from space, I copy it to the next available space in two space and fix the pointer. If I see something that already has been copied, I just fix the pointer. So, and I finish when all pointers in two space point to two space because I just go over all of two space and I fix the pointers. Sometimes I copy, sometimes I just fix the pointers. When I'm done and all of two space is pointing at two space, I finish the algorithm.
DFS.
Exactly. Yeah, it's like I'm doing a BFS and keeping the queue in two space. Yes. So what do I do with the pointer? If I look at the pointer in two space, I'm going over two space and fixing all the pointers. How do I fix a pointer? So if P is referencing an object, all of them are looking at from space because I copied the pointers that were in from space and looked at from space. And now if I copied that in two space, I look at it, it points to from space and I need to fix it. So if the pointer references an object with a forwarding pointer, so this object was already copied, then I just fix the pointer. I go over to space, I see something to an object that has been copied, I fix the pointer to where it was copied.
How do you know where to fix the pointer?
There is a forwarding point in from space.
With the two space, you leave the pointer.
Yeah, that I do. I always leave.
You need to leave it. You need to leave it.
Yes, yes. So if there's already a forwarding pointer, then I will just update it. If there is none, then it has not yet been copied. So what I do is I copy the object to where there is space into space. I record the forwarding pointer. Like you said, I have to do it myself when I copy. And then I update the pointer slot. Okay. So the entire collection cycle is stop all threads, flip from space into space, like what was to space becomes from space, and vice versa. And then I copy the objects directly reachable from the roots to space, and I can fix the roots pointers. And then I start scanning to space. So I go from the beginning. Whenever I see a pointer, then I do what I'm doing with the pointer. I take the object. If it's already copied, I just fix it. If it's not copied, I copy the object. I install a forwarding pointer in the old location, and I fix the pointer. So I scan to space and I fix all the pointers that point to from space. And when I'm done with everything, I'm done. Just flip the subspaces, scan the roots, and scan all pointers into space. That's Cheney's idea. And I just use 2 pointers for that, right? I have all the thing. I have a pointer to where I scanned already, and I fixed all the pointers. Let's mark it in black. These are pointers that are point to space. I fixed them already. These are pointers that I have not handled yet, and this is free space where I can copy more objects from space, from space. Sorry. So these are pointers I should go over, and this is free space where I can copy objects from space. So I just need 2 pointers. I don't need a mark stack. I don't need anything. Just 2 pointers as space overhead. Yeah. The order. You're worried about the order of moving the object. I will talk about it. It's the third thing we said: linearized order, linear order. I don't remember exactly how we called it. It's not sliding, but we'll get to that. You're right.
Why would there be a problem if you're always pushing something to behind it and then you reach that element?
It's like you bring the child next, but it's not like you're keeping the order that was in from space. That's the worry.
Are we putting all the things that are reachable from roots in like a stack kind of thing, and then going the person from the root, and then we can add his children to the end?
Right. But you agree it's not the same order that it was in from space. We don't keep the same order, and so it's not sliding like we wanted. So, but it will be okay. But, yeah. Okay, so this course started as a seminar, and there was a student who made these slides, so I will use them. They're nice. Look, this is an example of a heap from space. To space has free and scan pointers, which in the beginning are pointing to the beginning of the to space. Now I take the roots and I copy them to space. There's only one object pointed by the roots. It's A. And so what I do is I copy A here. Free space, the free pointer moves after A. The free space starts here. And scan is still in the beginning because I have not scanned the pointers that go out of A. And I leave a forwarding pointer. So we don't want to keep too many pointers in this picture. So I'll just write A prime here, which means the address of where A moved. A prime is the location of like the copied object. Okay, so this is a forwarding address. Cool. So I've copied all the roots. Now I have to go and fix all the pointers. So I start going. This is the first pointer. It points to object B that does not have a forwarding pointer, and therefore B needs to be copied, and the pointer then needs to be fixed, and I need to keep a forwarding pointer. So let me do that. Here I copied B, I fixed the pointer to point to the new location of B, and I kept a forwarding pointer that tells me where B was copied. Okay, so now I'm going to the second pointer in A, and it points to C. C was not copied, so I need to copy it, leave a forwarding pointer, and fix the pointer. Here it is, pointer fixed. I copied C to here, and I left a forwarding pointer saying where C was copied. Cool, so now I'm done with A. Let's mark it black. Okay, so I moved the scan pointer, I'm done with A. Okay, now let's go to the next thing to scan. It's the copy of B. So it points to D, because B pointed to D, so the copy still points to D. And I see that D has not been copied. So I have to copy it, I have to leave a forwarding pointer, and I need to fix this pointer. So here I do it. I fix this pointer to the copy of D. I leave a forwarding pointer in D. Cool. Okay. So I go to the next pointer in B. It points to E. It has not been copied yet, so I copy it. I leave a forwarding pointer and I fix the pointer to point to space, to the space copy. And now B is done, and I can move scan that I'm moving to the next object. Okay, I go to this object. C pointed to F and G. So I first go to F. It has not been copied. I will copy it and leave a forwarding pointer and fix this pointer to point to the space copy. I will go to this pointer that points to G. I will need to copy G, and I will have to fix this pointer and leave a forwarding pointer in G, and I'm done with C. So now I look at D. D has no pointers. So I can just go over it and mark it scanned. And then I go to E, and E has no pointers. So it's already, I can mark it scanned. And then I go to F. F has a pointer to A, which is now, you don't see it because there's a forwarding pointer here, but you can see here there's a pointer to A. I need to fix it. Now, A has been copied. Yes, it has been copied. So all I have to do is fix, according to the forwarding pointer, that F will point to the new copy. It was copied, I will not copy it again. And then there are no more pointers in F, and I can mark it as scanned. So F is scanned. G has no pointers, so I can mark it as scanned. And now scan is the same as free, and I'm done with the Chinese algorithm. Questions? Questions? Yeah.
החצים הכחולים כבר לא רלוונטי לנו, נכון? כי זה נמחק.
I don't care about from space. Yes, I don't look at anything here after I've done copying. And of course, in the next collection, I will move from here to here. This will become two space. Okay. Okay with the example. So why is it correct? So why is it correct that I've copied everything reachable and I've fixed all the pointers that are there? So yeah, I've fixed all the pointers because I went throughout everything I copied, but why did I copy all the reachable objects to space? Can anyone claim that?
The correctness of BFS and the way it handles the key.
If
We can see it in the two space.
okay, cool. If you prove the analogy to BFS, which is not very difficult because this is really the queue of things that you encounter, then it's fine. We know BFS goes through all the objects, but let's do it directly. Okay. So one thing to say is that let R1 be the set of objects directly reachable from the roots. I copy them in the first step. And then inductively, if Ri are objects reachable in I pointers, then I know that in the previous step phase, I have all R1 till Ri minus 1 copied. And since I go over objects in Ri minus 1, I will see all the pointers to Ri and I will copy all these objects. So inductively, I know no matter how many steps I need to, how many pointers I need to go through in reaching an object, I will eventually see them. But you can also look at a different view. So by the end, we know that root pointers point to two space and all the pointers in two space point to two space. So what I know is any path that I take from a root through the heap into another object will be in two space. So everything reachable from the roots is in two space. Okay, so this is like a direct way of saying that. But we have correctness, and now let's talk about the ordering that bothered you. So initially we said that if we just do arbitrary ordering, we're dead. The locality is destroyed and the program will run slower. In compaction, we usually had sliding or almost sliding order, and then it was excellent. And linearizing says that for each object, you move its descendants next to it. So, like here, 1, 3 was next to it, 4 was next to 3, and 2 was next to 4. This is fine if you have only one pointer in each object. But if you have several pointers, then it's not so perfect, the description here. And what copying does is it takes the children and moves them to the next available space. So this is basically linearizing, and in practice it works very well. So There's no locality problem when you do this. Because whenever you go to an object, many times you go to its descendants, you just follow pointers, and then they're close, usually, as much as it can be. Okay, so properties, space overhead, half the heap is wasted, it's reserved for the next collection, it's not good. But I don't need an auxiliary structure to like a mark stack, and I get compaction for free. So there are some good things about it. You will never want to have a large heap with a reserved copy. This will never happen in practice, but we will have cases where this will be good. So the complexity of the execution is proportional to the live data. If you have very few objects that are alive and I need to copy, this is excellent. So in terms of time, I will do very well. So this is called survival rate. If I have few objects that survive the collection, this is going to be very good. And now, in general, if I compare marking to copying, of course, marking is cheaper. You need just to, you don't need to copy an object. But here you just touch the live data. So if there are not many live data, then copying is going to be not so expensive. And mark and sweep needs to do sweep over the entire heap. And then if you sweep the entire heap, then you touch also the dead objects. And if there are lots of those, you're going to also suffer. And so you want to do copying when you have a small heap with very few live objects. And we will have cases like that, and we will see that it's excellent to use copying then. So it's simple, and the allocation is very efficient. It's called bump pointer or linear allocation. I have a large free space, and I just look at the pointer to do where it's free, and I move it to allocate. I say, you need 3 bytes, I move it 3 bytes. You need 64 bytes, I'll move it 64 bytes. This is very convenient to allocate when you have a consecutive free space. So it's very simple and efficient allocation. The good things in copying, and there was a struggle between them for a while. Today, collectors have various components in them, and some of them use this, some of them use that, and we'll talk about it more. Okay, there are some, there is code which I will leave in the slides, but I will not go over. And one thing that I want to talk about is the garbage collection efficiency. It should be intuitive that if you have larger heap, then it's easier. You use less time for the garbage collector. But let's do it once formally. So, okay, so suppose you have some space of reachable object. Maybe the program uses 100 mega of reachable objects. So for example, I don't know, the Technion has 15,000 students, so there is a heap that contains the information for these 15,000 students. Now, it's pretty stable, maybe today 100 new students come and tomorrow 100 students finish their studies and are taken out of this live memory. So in general, it's pretty stable. Of course, if you go 10 years from now, maybe there will be 20,000. I don't know. It may change. But as we look at it today, it's stable. There is a specific space that the program uses. Let's call it R. This is the space that the program uses. There is allocation, there is deallocation, but we have R words that are used. Now, when I do garbage collection, then Cheney will, let's call it CR steps in doing the copying. So C is something, how much time does it take to scan a word? You have to copy a word, and then you have to scan it to see if you have to copy its descendant. There is some time that it takes, let's call it C. That's the time I need to handle a word. So doing all the collection will take me C times R. So CR operations will take a full collection. Now say that the size of each semispace is M. So I have reserved M words, and I have in from space M words. Some of them are reachable, some of them are non-reachable object. And so the space that I allocate between two collections is m minus r. Let's see what it means. When I do a collection, I will copy the reachable r space to the beginning, and then I will have m minus r space to allocate in until I need to do a new collection. Is that okay? We agree. Cool. Okay, so what is now the cost of a GC per word that we reclaim? So I need to do all this work in order to move the live object. And how many words I allocate? I allocate this number of words before I need to do the next GC. So for each word I allocate, I have to do this amount of work. Okay? Questions, or this is clear? Okay, cool. So I have here the amount of work that I need to do. I don't control C. This is like a property of the copying algorithm. This is what it has to do. This is what it costs. And I don't control R. This is what the benchmarks want to use as its space. But I do control M. This is the size of the space that I work with. And if M is larger, then I will do less work per word of allocation. Right? So what happens here, if M is large, then it will take a lot of time until I need to do a collection. And the cost of the collection is fixed. It's the live objects. That's what the program needs. So if I have a huge semi-space, it will take a lot of time until I need to do this fixed amount of work. And then per word of allocation, this will be a smaller amount of work. Like I will do less work per allocated word if I have a larger heap. Is that okay? I don't know if it's too simple or too complex. The what? Yeah. It's amortized complexity in the sense that I count. I do a lot of allocation that come from a very short work, and then I do the garbage collection, and I split all the garbage collection word along into these words that I allocated previously. Yeah, cool. Yeah, exactly. So this is per allocated word, the amount of work that I need to do. And so now if I choose M to be large enough, so G becomes smaller and smaller. And there was a researcher who said that if you look at 14 times the size of the live space that you need, this is a huge heap. But then he compared it to a manual reclamation where you tell the collector to free whenever you need to free an object. And he said then it will be cheaper to use garbage collection than to use, in the amortized sense, it will be cheaper to use a garbage collection than to tell the system when to free each object. Okay? So this is the formal way to say that if the heap becomes larger, then you do less work per allocated word. And this should be intuitive because I can allocate a lot until I need to do garbage collection. And when I do garbage collection, it's a fixed amount of work. So if I allocate many words and then do the fixed amount of work, I allocate a few words and then do this fixed amount of work, it's cheaper when the heap is larger. Okay, questions? There is an example. Excellent. Okay, so look at this. Suppose, so I will look at a program that uses 100 megabyte of live space, and it's either using 700 mega or 350 megabyte of semi-space, and it allocates and free, free meaning objects become unreachable, and all through its execution, it allocates 1800 megabytes. So let's look at this picture. So so this is one semi-space and this is the other. Whenever I finish a collection, I copied the 100 mega of live words. And then I have, so this is the 350 megabyte semi-space. I have 250 megabytes that I can still allocate until the space is exhausted and I need to do garbage collection. And then I copy 100 megabytes to the other semi-space. And then I can allocate more 250 megabyte until I have no more space. Then I copy the 100 living object megabyte to the other semi-space and so forth. And so each time I do between collection, I allocate 250 megabytes. So to do 1800, I need to do like 7 of these. So 6 collections between 7 allocation periods, 1, 2, 3, 4, 5, 6, 7. And that finishes all the 1800 allocation megabytes that I need in the program. And I need to do 6 garbage collections. So, and I copy in these 6 collections 100 megabyte in each collection. So overall, I copy 600 megabyte. That's the cost of overall all the collections. Now, if I look at a larger heap, so suppose now the heap is 700 megabytes. Okay, in this case, I can allocate between collections. I start with this 100 and I can allocate 600 megabytes. And if overall in the program I need to allocate 1800, then if I each between 2 collections I allocate 600, then I only need 3 of these periods of allocations in order to finish the program. So now it is enough for me to do 2 collections to finish the program, and each of them I copy 100 megabytes. So instead of 600 megabyte copying, I do only 200 megabyte copying throughout the execution. And so I get that it's a lot more efficient. Like I increased the heap by 2, and I got that I decreased the overhead by 3 times. So increasing the size of the heap is very useful in making everything shorter. Okay, so if we look at how it worked, in 63, Minsky suggested copying. He did it in a complicated way. Fenichel and Jokelson did a recursive copying algorithm for Lisp. Cheney came a year later with his 2 pointers algorithm, and there are numerous variants that we'll see some of them in the course. So there are improvements, but they will wait for next week, and we'll see you then.